Bro, what are you doing?
I am making the intro for my next video titled Haloalkanes and Haloarenes.
Wait, what's the link between that and the good, the bad, and the ugly? Isn't that a movie?
Give me 30 minutes and you will see why this chapter is exactly like that movie. First, let me introduce you with the basics. That is, what is haloalkanes and haloarenes? Basically, if we replace hydrogen in an aliphatic hydrocarbon like methane or ethane by a halogen like chlorine, bromine or fluorine, we get alkyl halides, also called as haloalkanes. If we replace hydrogen in an aromatic hydrocarbon like benzene with a halogen, we get aryl halides, also called as haloarenes. Another key difference is haloalkanes contain halogen atoms attached to sp3 hybridized carbon atoms of an alkyl group. Haloarenes contain halogen atoms attached to sp2 hybridized carbon atoms of an aryl group. Haloalkanes and haloarenes may be classified as mono, di or polyhalogen compounds depending on whether they contain 1, 2 or more halogen atoms in their structures. Compounds containing sp3 carbon halogen bonds are classified into three types. First is alkyl halide or haloalkanes. The halogen atom is bonded to an alkyl group. They form a homologous series represented by CnH2n plus 1x. The second one is allylic halides. These are compounds in which the halogen atom is bonded to an sp3 hybridized carbon atom adjacent to a carbon-carbon double bond. The third one is benzylic halides. These are compounds in which the halogen atom is bonded to an sp3 hybridized carbon atom attached to an aromatic ring. Compounds containing sp2 carbon halogen bonds are classified as vinylic halides and aryl halides. Vinylic halides are the compounds in which the halogen atom is bonded to a sp2 hybridized carbon atom of a carbon-carbon double bond. Aryl halides are the compounds in which the halogen atom is directly bonded to the sp2 hybridized carbon atom of an aromatic ring. Haloalkanes can be further classified based on the type of carbon atom the halogen is attached to. In primary haloalkanes, the halogen is attached to a carbon bonded to only one other carbon atom. In secondary haloalkanes, the halogen is attached to a carbon bonded to two other carbon atoms. In tertiary haloalkanes, the halogen is attached to a carbon bonded to three other carbon atoms.
With so many compounds in existence, isn't it challenging to assign names to all of them?
Yes, there are countless chemical compounds and naming them can indeed be challenging. Apart from the IUPAC names, compounds also have some other common names. Common names are widely used because they are often simpler and more familiar than systematic names. Many compounds were discovered and named before standardized naming systems like IUPAC were developed. So their common names become deeply ingrained in scientific and everyday language. For example, water and ammonia are much easier to say and remember than their systematic names like dihydrogen monoxide and nitrogen trioxide, respectively. While common names are convenient, they can sometimes lead to confusion as they don't always provide clear information about the compound structure. In the common naming system, alkyl halides are named by first specifying the alkyl group followed by the name of the halide. For example, CH3Cl is methyl chloride, CH3CH2Br is ethyl bromide. In the IUPAC system, alkyl halides are named as halo-substituted hydrocarbons. The halogen is treated as a substituent and given the prefix fluoro, chloro, bromo or iodo followed by the name of the parent alkane. For example, CH3Cl is chloromethane, CH3CH2Br is bromoethane. For benzene with a single halogen substituent, the common and IUPAC names are identical. C6H5Cl is chlorobenzene, C6H5Br is bromobenzene. For benzene with two halogen substituents, common system uses the prefix ortho, meta and para to indicate positions. If the chlorine is at second and first position, it is called as orthochlorobenzene. If the chlorine is at first and third position, it is called as metachlorobenzene. If the chlorine is at first and fourth position, it is called as parachlorobenzene. IUPAC system uses numerical positions. For example, 1,2 dichlorobenzene is used for orthochlorobenzene. 1,3 dichlorobenzene is used instead of metachlorobenzene. 1,4 dichlorobenzene is used instead of parachlorobenzene. Dihaloalkanes are further classified based on the position of the halogen atoms into geminal dihalides and vicinal dihalides. In geminal dihalides, both halogen atoms are attached to the same carbon atom. In common system, it is named as alkylidine halides. Methylidine dichloride is an example for this. In IUPAC system, it is named as dihaloalkanes. Dichloromethane is an example for this. In vicinal halides, the halogen atoms are attached to adjacent carbon atoms. In common system, it is named as alkaline dihalides. Example, ethylene dibromide. In IUPAC system, it is named as dihaloalkanes. Example, 1,2 dibromoethane.
Why is the carbon-halogen bond in alkyl halides so important?
Great question. Halogen atoms are more electronegative than carbon. So the carbon-halogen bond in alkyl halide is polarized. This means the carbon atoms carries a partial positive charge while the halogen atoms carry a partial negative charge. This polarity makes alkyl halides reactive and useful in many chemical reactions.
Does the size of the halogen atom affect the bond?
Absolutely. As you move down the group in periodic table, the size of the halogen atom increases. For example, fluorine is the smallest halogen atom. Iodine is the largest halogen atom. Because of this, the carbon-halogen bond length increases from carbon-fluorine to carbon-iodine. For instance, the carbon-fluorine bond is the shortest and the carbon-iodine bond is the longest.
But how do we prepare these haloalkanes?
Alcohols can be converted into alkyl halides using several reagents such as concentrated halogen acid, phosphorus halides, thionyl chloride. Among these, thionyl chloride is preferred because the byproducts SO2 and hydrochloric acid escape as gases, giving a pure alkyl halides. The general equation for this process is ROH plus SOCl2 gives RCl plus SO2 plus HCl. For primary and secondary alcohols, a catalyst like zinc chloride is required. For tertiary alcohols, you can simply shake the alcohol with concentrated hydrochloric acid. To make alkyl bromides, we mix alcohol with hydrobromic acid and heat the mixture until it boils steadily. This replaces the alcohol's OH group with a Br group, giving us the desired alkyl bromide. Now, if we want to make alkyl iodides, it's a bit different. Here, we heat the alcohol with sodium iodide or potassium iodide in 95% phosphoric acid. the iodine takes the place of OH group. We get a good amount of the alkyl iodide. But here's something interesting. Not all alcohols react at the same speed. Tertiary alcohols are the fastest, followed by secondary alcohols and then primary alcohols. This is because tertiary alcohols form more stable intermediates during the reaction, making the process smoother. Sometimes, instead of using hydrogen bromide or hydrogen iodide directly, chemists use phosphorus tribromide or phosphorus triiodide. These are often made right in the reaction mixture by mixing red phosphorus with bromine or iodine. It's a clever way to get the job done without handling these reagents separately. To prepare alkyl chloride, we have two main methods. First, they can pass dry halogen chloride gas through a solution of alcohol. This replaces the alcohol's OH group with a Cl group, giving us the alkyl chloride. Alternatively, they can heat a mixture of alcohol and concentrated hydrochloric acid. The heat helps the reaction along and again the OH group is swapped out for a Cl group. But here's the catch. This method don't work for aryl halides.
Why?
Well, in phenol, the carbon-oxygen bond has a partial double bond character. This makes the bond much stronger and harder to break compared to the single bond in alcohol. Because of this, we need to use different, more specified methods to prepare aryl halides.
Are alcohols the only way to create haloalkanes?
No, there are a lot of other methods too. An alkene is converted to corresponding alkyl halide by reaction with hydrogen chloride, hydrogen bromide or hydrogen iodide. For example, when propene reacts with hydrogen bromide, two products such as prop-1-ane and prop-2-ane are possible, but prop-2-ane dominates due to Markovnikov rule. Addition of halogen is a classic way to detect double bonded alkenes. The reddish-brown color of bromine disappears, forming a colorless bis dibromates when ethene reacts with bromine in presence of carbon tetrachloride. When we react alkenes with chlorine or bromine under light or heat, a process called free radicals halogenation occurs. But here's the catch. This reaction produces a mixture of mono and polyhaloalkanes, which are hard to separate. For example, if we chlorinate a molecule like CH3 twice, CH, CH2, CH3, we get 4 different monochloroisomers because there are 4 types of hydrogen atoms that can be replaced. This makes the yield of any single compound quite low. Now let me tell you 2 important reactions where halogen exchange takes place. The first reaction is known as Finkelstein reaction, where an alkyl halide like chlorine or bromine react with sodium iodide to give alkyl iodide and sodium halide. The sodium chloride or sodium bromide thus formed is precipitated in dry acetone. It facilitates the forward reaction according to Le Chatelier's principle. Another important reaction is Schwartz reaction. Here the alkyl bromides react with silver fluoride to give product of alkyl fluoride and silver bromide.
Okay, but how can we prepare haloarenes?
Aryl chlorides and bromides can be easily prepared by electrophilic substitution of arenes with chlorine and bromine respectively in the presence of Lewis acid catalyst like iron or iron 3 chloride. Making aryl iodide is a bit more complicated. When we react an arene with iodine, the reaction is reversible. This means that the byproduct hydrogen iodide can react back with aryl iodide, undoing the reaction. To prevent this, we add an oxidizing agent like nitric acid or periodic acid. These oxidizing agents remove the hydrogen iodide, pushing the reaction forward and giving us a good yield of aryl iodide. Fluorine is too reactive to be used directly in electrophilic substitution reaction. It reacts explosively with arenes, making it unsafe and impractical. Because of this, special methods are used to prepare aryl fluorides, which we won't cover here. In another method, a primary aromatic amine dissolved or suspended in cold aqueous mineral acid is treated with sodium nitrate. As a product, a disonium salt is formed. Mixing the solution of freshly prepared disonium salt with cuprous chloride or cuprous bromide result in the replacement of disonium group by Cl or bromine. Replacement of the disonium group by iodine does not record the presence of cuprous halide and is done simply by shaking the disonium salt with potassium iodide. This method is also known as Steinmeier's reaction.
RJK. Since haloalkanes and haloarenes have halogens instead of hydrogen, does that change how they behave physically?
Alkyl halides are colorless when pure. However, bromates and iodates develop color when exposed to light. Many volatile halogen compounds have sweet smell. Small molecules like methyl chloride and methyl bromide are gases at room temperature. Bigger molecules with more carbon atoms are liquid or solid because they stick together more strongly. Halogen compounds are polar, meaning they have a slight positive and negative charge. This makes them stick together more strongly than non-polar hydrocarbons. Plus, they are heavier, which also increases their boiling points. So, chlorides, bromides and iodates boil at much higher temperature than similar sized hydrocarbon. For the same carbon chain, the boiling points depends on the halogen. Iodates have the highest boiling points, bromides come next, chlorides have the lower, fluorides have the lowest boiling point.
Why does this happen?
Because bigger halogens like iodine create stronger forces between the molecules, making them harder to boil. If the molecule is branched, it has a lower boiling point. For example, 2-bromo-2-methylpropane has a lower boiling point than its straight chain isomers because branching reduces how tightly the molecules can pack together. For dihalogen benzene, that is the benzene ring with two halogens, ortho, meta and para isomers have almost the same boiling points. But para isomers have higher melting point because their symmetrical shape fits better into crystals, making them more stable as a solid. Bromo, iodo and polychloro derivatives of hydrocarbons are heavier than water. The density increases with increase in number of carbon atoms. Haloalkanes are barely soluble in water because breaking water's hydrogen bond takes a lot of energy and a new interaction aren't strong enough to make up for it. But they dissolve easily in organic solvents because the force involved are similar, making the process much smoother. The reaction of haloalkanes may be divided into the following categories: nucleophilic substitution, elimination reaction, reaction with metals. The reaction in which a nucleophile replaces already existing nucleophile in a molecule is called nucleophilic substitution reaction. In this type of reaction, a nucleophile reacts with haloalkane, which is a substrate having a partial positive charge on the carbon atom bonded to a halogen. A substitution reaction takes place and halogen atom called the leaving group departs as a halide ion. Since the substitution reaction is initiated by a nucleophile, it is called as nucleophilic substitution reaction. It's one of the most important reactions of alkyl halides, especially when the halogen is attached to an sp3 hybridized carbon. This reaction allows us to swap out halogens for other groups, creating a wide variety of organic compounds. Common nucleophiles include hydroxide, cyanides, ammonia, and water. When these nucleophiles react with haloalkanes, they form products like alcohol, nitriles, amines, and more.
But what is the mechanism behind this reaction?
There are two types of mechanism. First, let me tell about SN2 reaction mechanism. SN2 reaction follows a unique one-step mechanism where the incoming nucleophile and the leaving group are both involved simultaneously. Imagine this. As the nucleophile attacks the carbon atom, the bond between the carbon and the leaving group starts to weaken. At the same time, a new bond between the carbon and nucleophile starts forming. During this process, the three groups attached to carbon, like hydrogen atoms or alkyl chains, started shifting away from the attacking nucleophile, similar to how an umbrella flips inside out when hit by a strong wind. During this process, the three groups attached to the carbon, like hydrogen atoms or alkyl chain, start shifting away from the attacking nucleophile, similar to how an umbrella flips inside out when hit by a strong wind. This flipping is called inversion of configuration. The reaction requires space for the nucleophile to approach easily. That's why methyl halides with just 3 tiny hydrogen atoms react the fastest. Primary halides also react well, but tertiary halides are the slowest because their bulky groups block the nucleophile's approach. So the reactivity order is methyl halide is greater than primary halide, and primary halide is greater than secondary halide, and secondary halide is greater than tertiary halide. In simpler words, the less crowded the carbon, the easier the SN2 reaction. The next reaction mechanism is called as SN1. SN1 reactions are quite different because they happen in 2 steps instead of 1. In the first step, the carbon halogen bonds break by itself, forming a carbocation and a halide ion. This step is slow and controls the speed of whole reaction. That's why we say SN1 reaction follow first order kinetics, meaning the rate depends only on the concentration of one reactant, that is the alkyl halide. Now in the second step, carbocation is attacked by the incoming nucleophile, which quickly bond to the carbon. The stability of carbocation determines how fast the reaction happens. Tertiary carbocations are the most stable, so tertiary alkyl halides react the fastest in SN1 reaction. Primary carbocations are the least stable, so primary alkyl halides react very slowly in SN1 reaction. SN1 reaction happen best in polar protic solvents like water, alcohols or acetic acid. These solvents help stabilize carbocation and the leaving group. The order of reactivity for SN1 reaction is tertiary halide is greater than secondary halide is greater than primary halide, and primary halide is greater than methyl halide. Interestingly, allylic and benzylic halides are also highly reactive in SN1 because their carbocations gain extra stability through resonance. Before knowing about the stereochemical aspect of this reaction, you need to know some basic terms. Some compounds can rotate plain polarized light. These are called optically active compounds. If the light rotates clockwise, the compound is dextrorotatory. If the light rotates anti-clockwise, the compound is levorotatory. A molecule is chiral if it is not identical to its mirror image, like your left hand and right hands. Chiral molecules are optically active. Enantiomers are pairs of chiral molecules that are mirror image of each other. They have identical physical properties but rotate light in opposite directions. Retention occurs when the 3D arrangement of groups around a carbon atom stays the same during a reaction. Inversion occurs when the arrangement of groups around a carbon atom flips during a reaction, like turning an umbrella inside out. Racemization occurs when a reaction produces a 50:50 ratio of mixtures of two enantiomers, making the product optically inactive. In substitution reaction, stereochemistry comes into focus in 2 ways. One, SN2 reaction. In SN2 reaction, the nucleophile attacks from the opposite side of leaving group, causing an inversion of configuration. If you start with an optically active alkyl halide, the product will have its configuration inverted comparing to the starting material. In SN1 reaction, the first slow step forms a carbocation, which is planar and achiral. The nucleophile can then attack from either side, leading to a mixture of products. This results in racemization, a 50:50 mixture of enantiomers, which is optically inactive because the rotation cancels out. Sometimes if no bond at the stereo center is broken, you might see retention of configuration. But in many SN1 reactions, racemization is the norm. When an haloalkane with a beta hydrogen atom is heated with an alcoholic solution of potassium hydroxide, there is an elimination of hydrogen atom from beta carbon and a halogen atom from the alpha carbon atom. As a result, an alkene is formed as a product. Since beta hydrogen atoms is involved in elimination, it is called as beta elimination. If there is possibility of formation of more than one alkenes due to the availability of more than one beta hydrogen atoms, usually one alkene is formed as the major product. The Russian chemist Alexander Zaitsev in 1875 formulated a rule which can be summarized as: in dehydrohalogenation reaction, the preferred product is that alkene which has the greater number of alkyl groups doubly bonded carbon atoms. For example, according to this rule, 2-bromopentane gives pent-2-ene as the major product.
Will they react with metals?
Yes, most organic chlorides, bromates and iodates react with certain metals to give compounds containing carbon-metal bonds. Such compounds are known as organometallic compounds. One such compound is alkyl magnesium halide, referred as Grignard reagent. These reagents are obtained by reaction of haloalkanes with magnesium metal in dry ether. In the Grignard reagent, the carbon-magnesium bond is covalent but highly polar. Grignard reagents are highly reactive and react with any source of proton to give hydrocarbons. Even water, alcohols, amines are sufficiently acidic to convert them into corresponding hydrocarbons. It is therefore necessary to avoid even traces of moisture from Grignard reagent. Another important reaction is Wood's reaction. Here, alkyl halides react with sodium in dry ether to give hydrocarbons containing double the number of carbon atoms present in the halide. This reaction is known as Wood's reaction.
Before sometimes you told me that haloarenes stubborn in nucleophilic substitution reaction. Why?
The first reason is resonance. In aryl halides, the lone pair on the halogen participate in resonance with the pi electrons of the benzene ring. As a result, the carbon-chlorine bond acquires a partial double bond character. This makes the bond shorter, stronger and much harder to break than a regular carbon-chlorine bond in haloalkanes. As we know, a stronger bond is less reactive. Next is hybridization. In haloalkanes, the carbon bonded to halogen is sp3 hybridized, but in haloarenes it's sp2 hybridized. Now there's the key difference. sp2 carbon has more S character which make it more electronegative and capable of holding electrons closer to itself. This results in a shorter and stronger carbon-chlorine bond in haloarenes. Now let's consider the phenyl cation. In haloarenes, if the carbon-chlorine bond breaks heterolithically to form a carbocation, the resulting phenyl cation is extremely unstable because this positively charged carbon cannot stabilize itself through resonance like carbocations in haloalkanes. Since the SN1 mechanism depends on carbocation stability, it's practically ruled out in the haloarenes. Finally, there is the issue of electron cloud repulsion. The benzene ring is electron rich, so when a nucleophile, which is also electron rich, tries to approach, it faces repulsion. This further reduces the chance of a successful nucleophilic attack. But interesting exception, chlorobenzene can be converted to phenol, but only under extreme condition, that is 623 Kelvin temperature and 300 atmospheric pressure. However, the presence of electron withdrawing group like NO2 at the ortho or para position dramatically enhances the reaction. This stabilizes the negative charge in the transition state, making the reaction easier. But if the NO2 group is at meta position, there is no such effect. But haloarenes like benzene can undergo reactions such as halogenation, nitration, sulfonation, Friedel-Crafts reaction. However, this reaction happens slower in haloarenes compared to benzene because the halogen slightly deactivates the benzene ring. The halogen is electron withdrawing due to its inductive effect, which pulls electron away from the ring. But it's also electron donating through the resonance, pushing electrons into the ring. This makes the halogen ortho and para directing. In other words, new substituents are more likely to attach at the ortho and para position relative to the halogen. The halogen's resonance effect increases the electron density at the ortho and para positions more than at the meta positions. This makes the ortho and para positions more attractive to incoming electrophiles. Because the halogen slightly deactivates the ring, electrophilic substitution reaction in haloarenes are slower than in benzene. As a result, these reactions often require more drastic conditions like higher temperature or stronger catalyst. Haloarenes, while reacting with metal, form two important named reactions such as phytic reaction, where aryl halides give analogous compounds when treated with sodium in dry ether. in which two aryl groups are joined together, and Wood's-Fittig reaction where a mixture of alkyl halide and aryl halide give an alkyl arene when treated with sodium and dry ether.
But wait, we started our conversation by discussing good, bad, and ugly properties of haloalkane and haloarene. Till now, you have not told anything about it. So are you making the intro as clickbait?
No. Okay. Now tell me the haloalkanes and haloarenes you know, and I will tell its good, bad, and ugly properties.
Dichloromethane.
Dichloromethane is an excellent solvent with powerful cleaning abilities. Its ability to dissolve stubborn substances make it invaluable in industries like pharmaceuticals, paint removals, and metal cleaning. Dichloromethane is toxic and can cause dizziness, nausea, and numbness if inhaled at higher concentration. Even mild exposure may impair hearing and vision. Prolonged or intense contact can lead to severe burns on the skin and eyes, posing serious safety risk in industrial settings.
Trichloromethane.
Chloroform is a versatile solvent, effectively dissolving fat, alkaloids, and iodine. Its major use today is in producing freons, an important refrigerant. Chloroform exposure can depress the central nervous system, causing dizziness, fatigue, and headaches when inhaled in higher concentration. Chloroforms can oxidize in the presence of air and light to form phosgene, a deadly poisonous gas used in chemical warfare. This is why chloroform is stored in dark bottles tightly sealed to prevent air contact.
Iodoform.
Iodoform was once valued as an antiseptic because it releases free iodine, which effectively kills bacteria and aids in wound healing. Iodoform itself isn't responsible for the antiseptic effect, it's the liberated iodine that does the job. Iodoform has a strong, unpleasant odor that many find intolerable, limiting its practical use in modern medicine.
Carbon tetrachloride.
Carbon tetrachloride was widely used in the past for various practical purposes, including as a cleaning agent, degreasers, and in fire extinguisher. It also played a crucial role in the manufacture of refrigerants and other chemicals. Exposure to carbon tetrachloride can cause dizziness, nausea, and vomiting. Prolonged exposure may result in liver damage, nerve cell damage, or even coma in severe cases. Carbon tetrachloride is a powerful ozone depleting substance. It releases into the atmosphere, contributing to ozone layer depletion, which increases the risk of skin cancer, eye disease, immune system disorder.
Freons.
Freons are non-toxic, non-corrosive, and chemically stable, making them excellent for use in refrigeration, air conditioning, and aerosol propellants. Their stability allowed industries to develop safer cooling systems compared to earlier, more hazardous chemicals. Despite their stability, freons eventually escape into the atmosphere. Due to their inert nature, they persist for long periods before breaking down. Once freons reach the stratosphere, they initiate radical chain reaction that destroy the ozone layer, increasing the risk of skin cancer, eye disease, and climate imbalance. This environmental threat has led to severe restrictions on CFC use worldwide.
PP. Dichlorodiphenyl. Trichloroethane. DDT.
DDT was life-saving insecticide that played a crucial role in controlling malaria and typhus outbreaks, significantly reducing the deaths worldwide. Its discovery earned Paul Muller a Nobel Prize in 1948. Over time, many insect species developed resistance to DDT, reducing its effectiveness. Additionally, DDT proved highly toxic to aquatic life, posing serious environmental risk. DDT's chemical stability and fat solubility made it accumulate in animal tissue. Bioaccumulation leads to its concentration increasing up the food chain, causing potential harm to wildlife and humans. The long-term risk led to DDT being banned in several countries, including the United States in 1973.
Bro, if the viewers watch till now, they might definitely subscribe to your video. Okay, next. What chapter will you explain?
Alcohols, phenols, and ether.